Hello, everybody, and welcome to Lecture 2 of Calculus 1, Summer Session 2. Um, today we're going to talk about tangent lines and secant lines, which are not exactly the same as tangent and secant in trigonometry. They're unrelated. It's sort of like Washington, D.C. and Washington State. They're both named for George Washington, but they don't necessarily have any particular relationship with each other any more than Washington, D.C. and any other state. So similarly, the idea of tangent and secant in trigonometry and the idea of tangent and secant in that we're going to be talking about, the calculus concepts of tangent and secant lines are named for the same thing. Latin tangent is derived from the Latin word for touch. Secant is derived from the Latin word for cut. And both of these, tangent and secant, as we're going to talk about today, and tangent and secant in trigonometry are named from these Latin words. But you can think of them as being totally different things, because if you try to read tangent and secant from trigonometry into what we're doing today, it'll be highly confusing and distracting. So we can just think of them as totally related. So when I say tangent and secant, don't think tangent and secant from trigonometry. And as we look at tangent and secant lines, we're going to begin to touch on or cut into, as the case may be, the first and one of the major central themes of this course and ideas, which is finding the slope of the tangent line. It's called the derivative. And just as we're doing that, we will need to introduce the notion of the limit, and the notion of the limit we'll dwell on the notion of a limit a little bit. And sometimes the limit is introduced before the idea of a tangent line, but it seems important to me because it was historically the limit was an idea that was come up with hundreds of years, actually, or at least 100 years, over 100 years, maybe even, I don't think quite 200 years, but it came much later than the idea of the derivative. So the derivative originally, Isaac Newton, when he talked about the derivative, he did not use this notion of a limit. He spoke in prose, and he said things like diminishing ad infinitum, and it was only later on Cauchy, who was Napoleon had a cohort of mathematicians who were very prolific, and then Augustine Cauchy, or I am not good at French pronunciations, unfortunately, it's probably all wrong, but Cauchy introduced this notion of a limit that we're going to be talking about that's standard in modern calculus courses in order to justify and make people feel safer with calculus. Because when calculus first came out, it was like, and especially before Newton, when it was in the works, it was met with a lot of skepticism, because there was this idea of an infinitesimal before limits were really defined. Many people thought in terms of an infinitesimal, which was supposed to be a quantity that is smaller than any positive number and greater than zero, which a lot of people found to be a very questionable concept. And even one person, Bishop Berkeley, who those of you who study or have taken philosophy classes might have heard of him. He was an anti-materialist or immaterialist, believed that everything in the world comes from the mind, but he wrote a treatise on calculus, and he criticized the idea of an infinitesimal, saying that, referring to them as the ghost of a departed quantity, which to me sounds very cool, but it was sort of a derogatory term, and a lot of people didn't like it. A lot of people still don't like the idea of an infinitesimal, but it has been revived, and you will find some fringe calculus textbooks that build everything up in terms of infinitesimals, which is, to reiterate, infinitesimal is the idea that it's some fixed quantity that's smaller than any positive number but greater than zero, which is sort of weird, but instead we're not going to be using infinitesimals, although they have left their impact on the notation that we'll be later running into in this class. But we will be using the notion of the limit, which is more of an idea of speaking of the shrinking process taking place, as opposed to a positive number that gets arbitrarily small, instead of positing that there is some number that is smaller than any positive number but not 0.
So here's a little refresher on what a tangent line is in a more perhaps visually appealing fashion than trying to do it on the board like I did yesterday. A tangent is a straight line that touches the curve. You could think of it as skiing down a hill, or balancing a ruler on the side of a wheel, whatever imagery you like. And this is, of course, a central piece of calculus. So looking at this expression, this is f of x0 is, of course, y0 in the classic expression that keeps coming up of y minus y0 equals m, x minus x0. You want to connect, you want to make a line, that's the point slope formula. You want to make a line that goes through x0 and y0 and has slope m. So this, for some reason that will become apparent in the next week or so, is the slope of the line, of the tangent line at x0 for this particular function. Now it might seem kind of frustrating. Why are we throwing around an x and an x0? The reason for that is that this tangent line is being plotted at a certain fixed point on the graph, and so x0 is that fixed point. So for example, right now, x0 is 0.22, but we could make it, for example, 0. Let's see, 0. There we go. We can make it 0, and that would be the tangent line at the apex of the semicircle, which of course intuitively we can tell. I mean, if you had a wheel and you put a ruler on it, on the very apex the ruler would be laying flat, so it has slope 0 at that point. And of course you can check with this formula. Sure enough, setting x0 equal to 0, we get the horizontal tangent that we would expect. So it's not immediately clear how we would approach finding this expression. There actually are geometric workarounds for the circle because the circle is so well understood. Like I said, I mean, even the ancient Greeks had some sense of tangents to circles. But let's say we have a more wonky shape like this, this bend in it. And let's just take the tangent line at 1, set aside x0 for a second by setting x0 equal to 1. So, and let's seek to find the tangent line. So this is the tangent line. There's a picture, spoiler. So this is again point slope. This line right here goes through the point 1 and f of 1, x equals 1, y equals f of 1, and it has slope f prime of 1. So f prime of 1, what is that, and why does it give us the slope? Well, f prime of 1 is the derivative. It's called the derivative, and it is what we're building up to. It's a function which gives us the slope to the tangent line to a curve at a given point on that curve. And Desmos has it built in because, Desmos has been programmed with calculus. And so just when I just gave it f, to be this curve, it automatically sets f prime to be equal to the slope of the tangent line to the curve. And then, so anyways, f prime is what we're building up to, and we're going to figure out how to find it for ourselves. Pretty soon you'll be able to find f prime for this function for yourself. But for now, we don't actually know how to do that, but I've just shown you this here. But the issue is, if we tried to make a first approach with algebra and precalculus, we would need to either know the slope, or if we didn't know the slope, we would need to know 2 points. Because if you have 2 points, you can use the rise over the run. You can translate it into a point slope form. You can get a direct expression for the line. So if only we had 2 points, but we only have 1 because the line only touches the graph at 1 point. But okay, so let's say we did have 2 points, and they were just 2 nearby points on the graph, so that doesn't look very nearby. Let's make it a little closer. So if we graph a line that goes through 2 points on the graph, and notice here, again, if it helps, pause and look at this formula to verify what I'm saying, but this here is a a line that goes through the points 1 and f of 1, and it also goes through the point goes through the point 1 plus h and f of 1 plus h. See, so these, and they make the point for us. So this is the red point, this is the blue point. And so this is called a secant line because it cuts the graph, it cuts through the graph, as opposed to the tangent line which touches it. Now, as h goes to 0, the secant line approaches the tangent line. It gets closer and closer to the tangent line, but just as we're hitting 0, it vanishes. Desmos doesn't like it going to 0, and the reason for that we can look right here. It's because we're getting 0 division. But it's sort of interesting because we're getting 0 division, and yet it's not going to infinity. Like, if you divide 1 by x, or 1 by h, 1 over h, and then h goes to 0, h gets smaller and smaller, 1 over h will get bigger and bigger, right? So like if h is going from 1/5 to 1/10 to 100th to 1,000th, then 1 over h is going to go from 5 to 10 to 100 to 1,000. It's going to blow up, right? H gets small, 1 over h gets big. So you think, yeah, at 0 division, usually the expression, if the denominator is going to 0, then the expression should blow up, right? Well, in fact, not necessarily. And to illustrate that, in an example that seems trivial and maybe even cheesy, let's look at expression x squared over x. And the notation that I'm going to use right now, and that we're also going to see and use over and over again in this class, is limit as x approaches 0. I'll stop and talk about that a little bit more in a second. But this means x is getting smaller and smaller. But this expression, technically, it's valid when x is not 0. But as soon as you set x equal to 0, it's no longer a valid expression because the x in the denominator is 0. You get 0 division, and that's not okay. And of course, this example is very cheesy because x squared over x is clearly x. And so it seems like, well, why do this is sort of a technicality to worry about this 0 division, because really the whole expression is x. We can just get rid of the division, right? There's no reason we need to be doing any division in the first place. And indeed, that is legitimate as long as x is not equal to 0, we can do the division and just get x. And so what this limit as x approaches 0 means, and I'll give you a precise definition in a second, but what this limit as x approaches 0 means is that x is never actually 0, but it gets arbitrarily close to 0. And because x is not 0, we can perform the division legitimately, and we get x. Well, now, the limit as x approaches 0 of x is of course just 0, because as x gets small, x gets small. I mean, it's circular, but yeah. So it seems like a excessively cheesy example, but we'll get to some more interesting examples, I promise. So the definition of a limit. So the definition of a limit. So we say L equals limit x approaches a. We set a equal to 0 before. As I said, abstraction, we're going to speak in generalities often. So, of course, this is general in the sense that a can be any number. It doesn't have to be 0. And
and L, again, we're going to have a lot of letters that could represent all sorts of different numbers. But the relationships between them are going to be given by our equation. So that's somewhat abstract, but it's also, I guess it's a life skill. I mean, I think that's why calculus is a prerequisite for a lot of things. Limit x approaches a of f of x if f of x can be made to be as close to L as we like, by making x as close, by making x close enough to A. So if we go back to the example, the graphing example that we were doing earlier, we were making x, and I'm not going to pull back up the video because it's or the graph, because it's sort of a frustrating thing to do with this whole recording thing. I have to pause everything and splice the videos together. But if you want to rewind and look back at the or I'll send you the Desmos graph so that you can play around with it. So if you look at we had the one picture where we had the tangent line, and h was going to 0, and the tangent line was approaching, or sorry, the secant lines were approaching the tangent line. So setting h equal to 0 was not valid because it led to 0 division. But by making oh, I didn't write x right here. I said it, but I didn't write it. By making by making 1 plus h, our x in that case was 1 plus h, and our a in that case was 1. So by making 1 plus h close enough to 1, in other words, making h go to 0, we were able to make the slope, which is L in this case, we were able to make the slope of the secant line arbitrarily close to the slope of the tangent line. So I introduced limits in this fashion because this is historically how they came up. This definition, modern mathematicians don't consider it quite rigorous enough. It's which I'm not sure. I mean, they don't like words like close, or you know, the language is considered too much prose for modern mathematicians. So they precisely do a whole bunch of stuff with these letters representing numbers that are getting smaller, but it's exactly the same thing. But this definition of a limit was actually come up with by Cauchy, who I believe I mentioned in the introduction, and Newton, of course, did not use this definition of a limit. And it was, the limit was come up with, the idea of a limit was invented exactly for the context we just talked about, which is why I brought it up. But of course, we could consider it in isolation from that context. And it turns out that as math progressed and went in different directions, this concept of a limit turns out to be interesting actually in a lot of other situations as well. And so now that we have the definition of a limit, and you might, I don't know if anyone wants to screenshot it, I'll just sit here with it for a second. Now that we have the definition of a limit, we can start talking about some other things with limits, and we can just take them in isolation and forget about the tangent line for a minute. I mean, of course, we're going to come back to the tangent lines. It's much of what this whole class is about, but just dwelling on the limit. So, there is an idea of continuity, and I'll illustrate what continuity is by showing a function that's discontinuous. Because if I just define continuity, it would be sort of like, come on, that's like too obvious. Isn't that always true? Well, it's not always true. There are discontinuous functions as well. Okay, so this is y equals the absolute value of x over x if x is not equal to 0. And is not defined at 0. So this function, we could say, well, what is the... Oh, and maybe I should write this in orange, so I forgot red is not very visible. So this function, we could say, well, what is the, let's call this f of x equals y equals absolute value of x over x. So what is the limit as x approaches 0 of f of x? And in fact, there is no limit, because you can make x as close to 0 as you want, and f of x will be 1. F of x equals 1, no matter how close you make it from the right. So if you come from the right, f of x will always be 1. So it seems like, okay, well, the limit must be 1, right? Well, no, because you can make x as close to 0 as you want from the left, and you always end up with negative 1. F of x equals negative 1. And so we have to say this doesn't exist. The limit doesn't exist. But we could talk about the left limit and the right limit. And the way that that's written would be written as limit as x approaches 0, and there's usually a plus inserted somewhere. Usually it's over the arrow, but sometimes people put it some other place, like over the 0, or they insert pluses in different places. But if you have limit and you have a plus somewhere in the mix in this limit expression, it means that you're taking the limit from the right. So in our particular situation, the right limit, it's often called the right limit of f of x as x approaches 0 is 1. And then the left limit, you might be able to guess exactly the same idea, only wherever you inserted the plus, now you instead insert the minus. Yeah, and the terminology for this is, this function is said to be discontinuous at 0. And so definition, function f of x is continuous at a if, and this is a as a variable, not a as part of my sentence structure. I'll put it in a different color to emphasize that. It's continuous at a if limit as x approaches a of f of x is equal to f of a. So this, for one thing, requires that f of a be defined. But it requires more than that f of a be defined, because if you think about it for a minute, the example that we just did, I asserted that 0 is not in the domain of the function, that f of 0 is not defined. But we could have defined f of 0 to be 1. It wouldn't make a difference. We would run into the same problem. The left limit would still, the right limit would, and you could call it right continuous, the right limit would still be, would equal the function. This would be true with the plus right there, but it would not be true with the minus right there, so it wouldn't be true. Because when we don't put a plus or a minus, recall we assume that if we were to put, whenever we don't put a plus or minus, that assumes the fact that if we were to put a plus or we were to put a minus, we would get the same thing, and that would be this thing. Yeah, so that definition is called continuity, and if you stop and think about it for a second, it's something that holds for the vast majority of functions that you've probably seen before, and you could visually, and depending on the pre-calculus course that you took, you may have already talked about continuity, but you probably talked about it in a more visual, intuitive way, and how that goes. So say this is A, and then this height right here is f of A. So this is, oh, red doesn't show up. This is the point A, f of A. So here, as x approaches A, this value is f of x, and f of x is clearly approaching f of A, right? The vertical coordinate of this point as x approaches A, the vertical, as x approaches A, the vertical coordinate f of x is clearly approaching f of A, and it would be the same if x was on the left or on the right, and this is intuitively captured by saying that there are no jumps. There are no jumps. So in our previous example, there very much were jumps, or there was one jump. And it was actually, you could, so that other function that we dealt with, this function, which is referred to as the step function, or actually it was the other way around when we did it last time. It was like this and this. It's referred to as the, or a step function. I guess there are some other step functions. But so this is a step function, and it has a jump right here. But everywhere else it's continuous. So, yeah, so I mean continuous sort of means what you would think it means is pretty much what that means to say, because that's, probably the word continuous, it's like colloquially, I guess, continuous just means that it keeps going. But it keeps going, as opposed to if it wasn't continuous, it would be disrupted, right? So this is a disruption. But it's not quite continuous, it's disrupted or discontinuous. Okay, so that is the definition of continuity. And then we touched on limits, and yeah, so now that we have this idea of limits in hand, I would like to revisit something from yesterday, which, most of this class will be revisiting things from the first lecture. So yesterday we talked about a square that is continuously growing, and let's call the length t. Say it's continuously growing in time. So this length is t, because why not? I mean, it's time, and then it's, I think, more evocative to think of it as time. So as time increases, the square grows proportionally to how much time has elapsed. So, initially the square wouldn't even be there, and then it would, as, say 1 second elapsed, it would be 1 inch long, and then as 12 seconds elapse, it would grow up to be this big. So, and we could ask, with what velocity is the square growing? And so if we increase the time a little bit by, say, h, we go to time t plus h, then we will have moved from a square with area t to a square with area t squared to I'll highlight the bigger square in orange, to a square with area t squared, t plus 1 squared, right? Because now we have t plus h squared, because now we have side length t plus h. And of course, we could have just done this algebraically, but I like to draw the picture and do the algebra. So now we have a square with area t plus h, and if we wanted to know the velocity of the change, we would take the new area, which is, let's call the area a of t. So the new area would be a of t plus h, and we would subtract a of t, and then divide by h. So change of area over change of time, which is, a velocity or a speed of something is how fast is the thing changing over time. And so this would be a velocity, but to get the instantaneous change in the velocity, we would want to have h approach 0. And of course, since a of t plus h is just t plus h squared, a of t is just t squared, what we have here is t plus h squared minus t squared over h. And using the FOIL method, we can turn this into t squared plus 2h plus h squared minus t squared over h. And the t squared terms cancel out, because one's plus, one's minus. And what we end up with is just, I forgot the t right here, 2ht, right? Because when we FOIL, we need to keep the t around. So this is 2th, but then this h cancels with this h. This h cancels with this h, so this term leaves a 2t, and then h squared over h, this just leaves an h. And then if we take the limit as h approaches 0, then, of course, we never set h equal to 0, because this expression is no longer valid if we set h equal to 0. But we take the limit as h approaches 0. So use this computation right here, and then it shows us that the limit as h approaches 0 of a t plus h minus a of h, minus a of t divided by h equals limit as h approaches 0 of 2t plus h. And of course, as h goes to 0, h disappears. So this is just 2t. And 2t is obviously, a valid expression even when h is at 0. There's no 0 division by h because h doesn't even show up in the expression. So yeah, so this is kind of cool. It tells us that the instantaneous rate of change. So we now have we can pretty much say we've done the first calculus of this calculus course just now. We've determined that the instantaneous rate of change of the square as it grows is 2t. And as I mentioned yesterday, you can imagine it as it's instantaneously growing outwards. It's like the lines are moving outwards, and this line has length t, this line has length t, it's growing by 2t. You can imagine it that way. Yeah. So this could be viewed alternatively. Say that we graphed call this the t-axis and this the a-axis. And hopefully after the last homework problem and the recitation and from recalling things from previous classes, hopefully you're all comfortable at this point with the fact that we can relabel these axes. I mean, we oftentimes will have this be the x-axis and this be the y-axis, but we can of course name them different things and have different quantities. So then going back to our expression before, a of t equals t squared. So we graph it, and we just end up with a parabola, right? And our preliminary expression when h was not 0 was the approximate rate of change, the rate of change over a time h, not the instantaneous rate of change, but the rate of change over a time h, was a of t plus h minus a of t over h. So, for example, we could pick a t value. This is always, I always prefer doing this on Desmos over doing it on chalkboard. But you could pick a t value, say right there, and then pick h, and so this is t, and this is t plus h. Then using the point slope formula again, or the point formula technically, this right here is the line going through these 2 points, and it has this as its slope. If you go back to that formula, I won't write the full formula, but if you go back to that formula, this is the slope. And at this point, if you want to pause the lecture for a second, at this point you might want to, if you're feeling a little bit confused about my bringing back the point slope and everything, you might want to try rewriting everything with t replaced by x and a replaced by y in order to bring it back to something familiar. In fact, you might want to do that anyways, unless you're comfortable. It's always a good thing to be really solid on, because it can be, when a calculus class is just chugging along, especially in the summer, where we're just going and going and going, it can be easy to forget the definitions, the foundations of even the language of what we're doing, because you just got to go and go and go. So it's in the going and going and going and doing stuff, it's helpful to keep drilling. Yes, we can relabel the axes and be able to bring up expressions like the point slope form and everything when you have a and t instead of x and y. So this is the slope of this line, and this is a secant line, as we were just talking about before, and then you take the limit as h approaches 0, And you do the exact process that we talked about before for getting the tangent line. So, yeah. So, and actually, what this can be restated. So I said before that this thing is called the derivative, and now I can give you the definition of the derivative. The definition of the derivative f prime of x is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And then what this says, of course, to put it into words, so mathematicians often like to, they prefer to have everything be very symbolic and abstract and drained of meaning, but if you put it back into words and put it into geometric pictures, what it's saying is that the tangent line, that this is the slope of the tangent line, because this is the rise over the run in the expression for the secant lines that we were talking about earlier on Desmos. And this could alternatively write this as limit w approaches x of f of w minus f of x over w minus x. This is just by doing the substitution w equals x plus h, which maybe makes it more familiar, maybe not. Maybe it helps, maybe it hurts. Either way you want to do it, these are exactly equivalent expressions. So that's the derivative. So now you know what the derivative is. Or maybe you already knew earlier in the lecture, in last lecture. But now you know how you are one step closer in tangibly being able to work with it. And if we rename a to y and t to x from the last example, like I mentioned, we already have a derivative rule, which is that if f of x equals x squared, then f prime of x equals 2x, which of course we had it before. We had it t squared and we had 2t, but we can of course rename it and all the commutations go through the same. So this prime, it would be really awkward to directly say, you could say x squared prime, I shouldn't write it there because I'm writing a false statement now, but you could say x squared prime equals 2x. You could use that terminology. Another terminology that you'll probably use, or probably see used and use, is d over dx, or dx squared over dx equals 2x, or d over dx x squared equals 2x. And this especially is very suggestive in that it appears to be a ratio. And if you remember, it's not a fixed ratio because we can't set h equal to 0. That would lead to zero division. But if you accept the infinitesimals that I mentioned earlier along, it is an acceptable ratio because h it's not 0, so zero division is not a problem. It's just infinitely small. It's a quantity that's smaller than any positive number, which of course, don't worry about the infinitesimals. The infinitesimals are, well, we're not going to be presenting things in terms of infinitesimals, so they're just going to be, I don't know, I mean, maybe do worry about them if you find them interesting, but don't be confused because I'm bringing in infinitesimals. I'm just bringing them in as a side note and a historical note. And that's where this notation comes from, is from these infinitesimals. Yeah. So, there is our first differentiation rule, and it actually was not the simplest differentiation rule. The simplest differentiation rules are probably the two following. So, a constant function, say, f of x equals 1. Constant function, well, what's the slope of the tangent line? The slope of the tangent line is just 1. Or we could write, limit as h approaches 0 of f of x plus h minus f of x over h. Well, this is just going to be 1 minus 1, so this is 0. This is 0 for any h. So this expression is exactly 0 for any h, because h is not 0. When h is not equal to 0, there's no zero division problem, and this will always be 0. So this is sort of in some senses the simplest example, is the simplest derivative, but it also, by being so much more simple, it requires keeping our wits about us. It's like sometimes it's easier to understand something complicated than something simple, because when you deal with something really simple, it's like it seems like there's no content in the statements, or it pushes on some weirder thoughts. So this is a thing to keep in mind with limits. This raises a possible point of confusion with limits, that this is 0, and the zero division here doesn't matter, because this is, as long as at any point before we get to, say this is x, at any point before we get to x, this is x, this is x plus h, the secant line is exactly this line. It's a line with slope 0. So if you think about it geometrically, there's nothing really confusing. But here, if you move into the more abstract algebraic picture, then you have to step back and think about, wait a second, this is identically 0, but this is not 0. It's just going to 0, but the whole expression is just going to be 0 the whole time. So the limit is 0. So f prime of x is identically equal to 0 when x is, when f is a constant function. And probably the next simplest case is a linear function, a straight line function. So if y equals mx plus b, if f of x equals mx plus b, then f prime of x equals m. And this makes sense because a straight line, is everywhere tangent to itself, or the slope of the line tangent to it is exactly itself, and m is the slope. So this is if you define the derivative as being the slope of the tangent line, then it's self-evident that it's this m, and then of course you could go through the computation as we've gone through them before, and maybe I'll do it just because the repetition can help. So f of x plus h minus f of x over h, limit as h approaches 0. Which is f of x. So this is going to be m times x plus h plus b minus mx plus b all over h. Now the b's are immediately going to cancel, and the mx's are also going to cancel. The mx's are also going to cancel here, right? And all we're left with, then, these b's have disappeared, the mx's disappeared. All we're left with is the mh. And we have mh over h, that's just m. Oh, I did something sloppy, which is not a good thing to do. I dropped the limit sign when really we're still taking the limit. Which is a bad habit. It's imprecise language. It's something that calculus instructors and graders are only expected to take points off if you don't do it. So I shouldn't be doing it. If you weren't to do it on a test or something, it's customarily understood that we're supposed to take off at least a point or two if someone drops a limit sign. So yeah, I should do it, and no one else should do it. Except when you've actually evaluated the limit. So once you've evaluated the limit, that's the point where you have manipulated the expression to a point where there's no longer any ambiguity or any problem with the zero division. So like, for example, going back to our cheesy example from before, or actually, let's make it a little bit less cheesy. Let's make it apparently more interesting, even though it's exactly the same idea. Of x squared minus 1 over x minus 1. So this is, you can't just plug in x equals 1 because we would get zero division. But the top's also going to 0. And if you like if you like polynomials, you like quadratic polynomials, you like factoring them, you might remember that this is x minus 1 times x plus 1. So then we can factor the x minus 1s out of both sides, and we're just left with limit as x approaches 0 of x plus 1. Of course, now we no longer have an ambiguous expression. We have an expression that we can evaluate unambiguously. The x disappears, so it just equals 1. Yeah. And a couple important limit laws, which I guess I'm not going to prove because we're not really proving things in this class, but I'll argue for. So a couple of limit laws. W approaches x of f of x, or sorry, of f of w plus g of w equals limit w approaches x of f of w plus limit w approaches x of g of w. That is, provided that both of these two limits exist. Provided the two limits exist. And so pretty much what this addresses is, like, for example, if these two limits don't exist but they cancel each other out. So like, for example, if g equals minus f of w, if g of x equals minus f of x, then this expression will always cancel to 0, and so the limit will just be 0. But 0 doesn't equal nothing, and it doesn't equal not defined plus not defined. I mean, 0 is just 0, it is defined. So, yeah. So that's one limit law. And the next important limit law is that A is any fixed number. A is any fixed number. Then limit w approaches x of a times f of x, or sorry, a times f of w equals a times limit w approaches x f of w. This is called the multiplication law. The last one was called the additive limit law. This is called the multiplicative limit law. And the next limit law is has even more qualifiers than the multiplicative one, and that's than the additive one, and that's the division one. Well, actually, before the division one, let's do the multiplicative one. So, if limit w approaches x, f of w, and limit w approaches x of g of w both exist, then limit f of w times g of w equals limit w approaches x f of w times limit w approaches x g of w. Yeah. And there's another law that is the division law of limits. So if furthermore I'm gonna so this is the multiplicative law. I'm gonna erase this so I have more room. The glare unfortunately restricts the board space. So this is the multiplicative law. Now I'm gonna write the division law. If these both exist and g of w g of x is not equal to 0, then f of w, limit w approaches x, of f of w over g of w equals limit w approaches x of f of w over limit w approaches x of g of w. So yeah, and as if you take any more math classes, and maybe even in this class, as you'll often need to remind yourself, we all need to remind ourselves of it, that just because implication flows one way does not mean that it flows the other way. So it could be very well be the case that these two things do equal each other, even if g of x does equal 0. And in fact, that is the case with the derivative. But it would require further analysis to arrive at that conclusion. It's not automatically true. Yeah. So, and this is something, limits of ratios and ratios of limits, is something that we're going to revisit at the end of this class with L'Hopital's rule. Limits were invented just to be able to define the derivative. But then once they started to be studied and used, people discovered other places that are interesting. So then other more sophisticated techniques were developed to evaluate limits. So stated all the limit laws that we're going to state for the moment. And I'll give a few examples before giving more definitions of things, more laws derived from limits. So I'll give a couple examples. And one is a limit that blows up to infinity. So limit as, and I alluded to this earlier, but limit as, say, h approaches 0, 1 over h, well, this blows up to infinity. I mean, for example, we could graph it. And if you want, it feels better to have it equal to x when we're graphing it. The graph of this function, you could graph it on Desmos, maybe you've seen it before, you could plug in a couple points, plugging in a couple points would be good. The function, let's plug in a couple points. This is 1/2. 1 over 1/2 is 2. 1/4 is 4, about twice as far out. And then 2, we have 1/2. 4, we have 1/4. So there's some points, and then connect the dots. And this is an asymptote. Hopefully, well, I'll review asymptotes in a second, but you've probably heard of them before. So the limit as x approaches 0 of 1 over x is infinity. And that is exactly the definition of an asymptote. Of a vertical asymptote is that the function goes to infinity in the limit towards that vertical asymptote. So terminology-wise, would we say that this limit equals infinity, or would we say that the limit doesn't exist? It sort of depends, and people get uncomfortable with infinity, kind of like they're uncomfortable with infinitesimals. It's like infinity is a thing that's used in a lot of rigorous mathematics, but then, of course, people also feel it has a sort of a less certain status among mathematical symbols. So sometimes people say that this limit doesn't exist if it goes to infinity. Sometimes they would say it goes to infinity. I think the textbook will just say this. But then it's splitting hairs whether the limit exists or whether it's infinity. It's sort of a matter of notation, a matter of language. But another thing you could say is you could evaluate a limit at infinity. So you could say limit as x approaches infinity of 1 over x equals 0. The definition of this is just that x is getting really, really big. Because if you went back to the definition I gave you of a limit before, you would say, well, this means x getting close to infinity. But how can x get close to infinity? X is always, no matter how big something is, it's always infinitely far away from infinity. If something's infinitely far away and I drive 1,000,000 trillion miles in the fastest possible spaceship to get there, I'll still be infinitely far away because it's, infinity minus a trillion is still infinity. So x is never getting close to infinity, but when we say x gets close to infinity, we actually just mean that x gets big. So there's an example. So to underline the point about the division rule for limits, for how a limit could fail to exist when both go to 0, let's consider another thing that I brought up earlier, which is limit as x approaches 0 of the absolute value of x over x. So both of these limits, both the limit as absolute value of so this we know does not exist. So DNE is the language you'll often see, and that we'll use in this class for an abbreviation you can use for does not exist is DNE. As we mentioned before, right? The left limit is -1, the right limit is +1. But limit x approaches 0 of absolute value of x over the limit as x approaches 0, x. This is 0, this is 0. So we get an issue of 0 over 0, which is no good. Limit does not exist. So then you might say, well, what's the problem? If the limits don't exist, then the ratio of limits won't exist either, right? Or that if it's a 0 over 0 limit, it just doesn't exist, right? Disregard the last sentence I said. If it's a 0 over 0 limit, then you might just think if it's a 0 over 0 limit, then it doesn't exist, right? Because 0 over 0 is not well defined. Well, it's not quite that simple, because if we put it this way, this limit is most certainly 1. This equals 1. But this still doesn't exist. It's 0 over 0, but the limit does exist. And actually, all the derivative examples that we've been doing, also, the numerator goes to 0, the denominator goes to 0, but the result does not go to 0. So, all the limit laws immediately lead to corresponding derivative laws, because the derivative is a limit. Well, I shouldn't say all of them, because the product one doesn't quite. So you have to, nor does the quotient one. But the scalar multiplicative one does immediately lead to a rule, and the additive one does immediately lead to a rule. So f plus f of x plus g of x prime, and there's different notations of this. Right, f plus g prime of x. This equals prime of x plus g prime of x. And of course, what we mean by f plus g is the function which is f of x plus g of x. For those of you like exact precision, I will write the definition. So f where f plus g of x equals f of x plus g of x. So this is the additive law of derivatives, and it follows by just writing out the limit expression. So limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x plus g of x. So this thing equals all this over h. But of course we can just move this over here. Then we'll have g of x plus h minus g of x. So then we can split it up into the expression for f prime, the expression for g prime. And if you want to do that, you can. I'm running out of board space and time, so I won't do it. But if you want, feel free to pause and do the computation. And then we have multiplication by a number, and I think I may have called multiple limit laws multiplicative. So, and it is terminology-wise, it is sometimes done, but and that's why I was using the word scalar multiplicative, which is probably a word you're not familiar with, but what I was calling the scalar multiplicative one is this one. So I don't know what terminology the book uses to distinguish the two. You could check it out if you want. But this immediately yields by the exact same thing we were doing before. You just write out the limit definition of the derivative, and this will immediately yield a derivative rule, which is that a f prime of x equals a times f prime of x. Yeah, where by AF we mean A f of x. A f of x equals A times f of x. So if this terminology is confusing you or getting under your skin, this a notation, we could consider a concrete example. It's like a x squared prime equals a times 2x. So, yeah, so that is sort of crash course on limits, and we've defined continuity, we've defined the derivative, and introduced a few laws, and we can compute a couple more derivatives. That's the next thing to do, is to compute some derivatives, compute some limits. Computed some limits already. There'll be more limits in the homework, and going forward there will be some more limits. But now let's compute another derivative, because the only derivative we've computed so far is the derivative of f of x equals x squared. But let's branch out a little bit. So how about f prime of x, say f of x equals x cubed, what is f prime of x? So, as I've mentioned before, and as was in the last worksheet, this f of x equals x cubed is, as the name suggests, you could say, well, it's x to the third, but as x cubed, it's the volume of a cube with side length x. And so I said something in the first lecture that we're about to come around full circle to. So f prime of x equals limit as h approaches x of x plus h cubed minus x cubed over h. This, we can just expand it out. And expanding out an expression like this could be sort of tedious at times until you learn the rules for it. Then it's kind of fun when you have x plus, you have one thing plus another thing, x plus h raised to different powers. But if you know the rule, or if you've sat down or if you just sit down and do it, what you'll end up with is x cubed, just algebra. And you've probably seen it in algebra before, x plus h cubed. You just sit down and do all the algebra. We get x cubed plus 3x squared h plus 3x h squared plus h cubed. That's just this expression right here. All of this minus x cubed all over h. Oh, and I did the bad thing again. I forgot to write limit as h approaches 0. Oh, and this again, this should be a 0. It shouldn't be an x. Sorry about that. Limit as h approaches 0. Right thing. Okay. So these two things cancel. And what we're left with, this h cancels with this h, so we get 3x squared plus 3hx plus h squared. And these two terms disappear as, I probably won't take points off your exams if you forget to write the limit here and there. I mean, because it's so easy to do. But definitely don't disregard limits. It's not good to not write limits. Yeah, I mean, a mistake here and there is forgivable, but don't constantly do it. And always check yourself if you forget to write the limit thing. So this, the 3hx plus h squared vanishes, and we're just left with 3x squared. And so this actually comes back to something, as I said, that I talked about yesterday, which is that just as with the growing square, we can imagine it as like 2x or 2t in the other example, that it's the two lines growing outwards, because x is the length of the line. So here, x squared is the area of one of the surfaces of the cube, and as the cube's growing, you have these three faces growing outwards, these three square faces. Did I say the surface of the cube? Each square on the surface of the cube. X squared is the area of each square on the surface of the cube. and you fix one side of the cube, and the other ones are going out because the surface area of the whole cube is 6x squared, right? But just half the surface is growing out if x is increasing in the direction. So so you can, that's a way to remember or to think about, to conceptualize this derivative and the derivative of x squared. So with x squared, well, there's two lines on the side, and so it's 2x, and then with x cubed, there's 3 squares, and they're growing out, so it's 3x squared. So this actually leads to a more general rule called the power rule. And the power rule, when we do the product rule, we can prove it another way that might be more satisfactory to some, might be less satisfactory to some, but I'll go ahead and prove it or present it in one way, which is so say f of x equals x to the n, where n is some whole number, so 1, 2, 3, 4, 5, any whole number, any positive whole number. It's going to be different for negative whole numbers. Well, actually, that's not quite true. It will be different for 0. It'll be the same for different reasons. Well, for kind of the same reasons for negative numbers. But for now, let's just stick with the positive numbers. So let's see if we can get something intelligible trying to take the derivative of this. So f prime of x equals limit as h approaches 0 of x plus h to the n power minus x to the n power over h. And now this expression is kind of like, well, what do we do with that? Now, what's kind of cool here is that if we stop and think for a second, remember back to the computations that happened before. Glitch. So if we stop and think back to the computations from before, as I said, it's the last word. So if we stop and think back to the computations we did before, whenever there's a power of h that's 2 or greater, then that stuff is all going to disappear. And think about this polynomial. What this is you multiply x plus h times itself n times. So n times, right? So if this was 4, we just fill in one more x plus h here. If there's 5, we fill in a 5th one. So x plus h multiplied times itself n times, right? So this equality is this from here. So this limit h approaches 0 So if we start thinking about the terms here, we're going to have x times x. There's one time in our multiplication process we're going to take all n of the x's out, but then that's going to be canceled by this. So we're going to have x to the n, but that's going to be canceled by this. But then the next thing we could do, other than taking all the x's out, is wait, I need to plug in the computer. What we could do, other than taking the next thing we do, other than taking all the x's, is we could just take a single x or sorry, take just a single h and have all the rest be x's. So say we take the h from this one, all the rest of them are x's. So then we would get h times x to the n minus 1, right? But then we could also take this x and, or sorry, just this h and then all the rest of them would be x's. And then we'd have 2 times h times x to the n. Or we could do that. We could take just a single h from any of the given terms and all the rest would be x. And we would add all those things together and we get n times h times x to the n. And now the beautiful thing is that computer's not. Yeah. Oh, there we go. So now the beautiful thing is that any other way we do it, we're going to take at least h's because we've already exhausted all the cases where there's less than 2 h's. Right? We took the case where there's no h's. We took the case where there's 2 h's, or sorry, where there's 1 h. And all the rest of them are going to have h squared terms. So, erasing these from one room. We'll have plus h squared times something. And it doesn't matter what, because that something isn't going to have anything, going to infinity. It's this whole term here certainly is going to go to 0. So this equals n times x. All right, one more step. Limit h approaches 0. N times x to the n, because these two h's cancel, plus, and then this h cancels with the squared, so it's just h times something, plus, h times something, and this goes to 0, and so we can just evaluate the limit. The limit is just n x to the n. So we evaluated the limit, and we just get that this derivative f prime of x equals n times x to the n. And now it's totally fine if you didn't follow this derivation of the general power rule. I know that this idea of analyzing the algorithm without actually carrying it out, just saying what would happen if we did it, parts we can ignore. That it might be sort of abstract, or maybe not. It's sort of algorithmic thinking. Any of you, I don't think there are any computer science majors here, but it's sort of that type of idea. Also, if any of you are really interested in this type of stuff, you could look up Pascal's triangle and the binomial theorem, and that breaks down this whole algorithm thing into all the detail we would need to have an explicit expression. So, of course, that's not at all required for this class. It's sort of advanced, the binomial theorem and Pascal's triangle, but it's cool stuff. So if anyone's really likes math and wants to have something fun to look into, there's a recommendation. But if you didn't understand this derivation of the power rule, it's not a big deal, because like I said, the general power rule, we're going to show the power rule again once we've developed what's called the product rule of differentiation. So of course, everything else in the lecture, you really should, hopefully understand. But this last part we'll do again, so it doesn't the last part meaning the power rule for the general n, we'll do again. So that's it for lecture 2, and enjoy the rest of your day.